Yeah, my name is Michael Kluge. I'm working on our site Dresden on parallel file systems. Most times I'm analyzing file systems. What I'm talking today about is a testbed. Alcatel Lucent has produced the first commercial available 100 gigabit equipment where they can transmit 100 gigabits a second on a single wavelength. They've asked us if we want to participate in a testbed, and sure, we wanted. We scheduled like insane number of different tasks on that testbed. We had at first native TCP bandwidth tests. We had parallel file systems, actually 3 different parallel file systems. Lustre was just one of these. We had video conferencing as, you know, a side effect of other tests, or as an overlay to other tests. We had virtual machine images on the testbed. And in our project, we tried with Lustre to at first reach a maximum bandwidth. Then Indiana, in particular, Steve Sims and Robert Henschel were interested in modeling Elnet performance and getting you know, a clean look onto a Elnet. And I was interested in how small file I/O, how interactive small file I/O can be in a WAN environment. So that's a testbed we got. That's what Alcatel Lucent and T-System provided. Initially, we had some equipment in Dresden, some in Freiburg. 60 kilometers is a you know, bit more than a real distance between the 2 places. On both ends, we had an optical layer and the router attached to it. The router had, at the end, 20 10 gig uplinks. We had the rack of HP file servers, and DDN shipped us 2 S2A9900 and 1 SFA10K. So we were actually able to compare 2 A900 with 1 SFA, and we also connected on each side a local compute cluster via InfiniBand to each IB server. So for us, from a parallel file system perspective, this actually we're not interested in all the networking stuff. We just know there is a 100 gigabit line, and as the switching is done on layer 2, for us this looks like we had like 32 nodes on a single subnet. So we had like one homogeneous cluster where a couple of nodes have a different latency than other nodes. That's how the testbed looked to us. The bandwidth we could achieve on these nodes. Oh, I missed to change the titles. Still some German in it. The bottleneck here is clearly the 100 gigabit link, so you can transmit about 12.5 gigabytes a second in a single direction. And as we know from the Bandwidth Challenge 2007, you need to do your tests or your peak bandwidth, you go for both directions. So in the end, we were actually shooting for 25 gigabytes a second over this testbed in our Lustre setup. So these are, yeah, many thanks to DDN. They shipped like, I think we have here 3 pallets. In the end, I think we had like 4 or 5 pallets of gear that they shipped to us and got back like, I think 1 or 2 weeks ago. We had this here for almost a year, and yeah, worked very reliably and showed good performance. For DDN, it was also interesting to compare these 3 file systems on a single on the same hardware. For us, it was a challenge because everyone wanted to be the fastest, or wanted to get just the highest number on the file system. At the end, GPFS, and they were more interested in, study if they can deploy a file system at the WAN with this equipment. They didn't actually shoot it for high numbers. We got. This is the setup how we were trying our peak bandwidth experiments. So from a cluster in Dresden, we used the rack in Dresden as Lustre router to write to Freiburg. And from the Freiburg cluster, we used the rack that's also always acting as a storage server for the DDN devices here. We were writing to Dresden, and hopefully, the idea was to saturate the link in both directions. What each of the AHP servers had to do is routing from the local cluster to the other side, do some Elnet routing, and for the local DDN gear to get the data in from the other side and write it to the local disks. To avoid any NUMA issues in that environment, we decided to use a larger number of nodes and use only a single chip with 6 cores and a single interface. So single 10 gig east, single InfiniBand link, and single fiber channel storage link. So to avoid any scheduling issues, just to get to the target point or get your number earlier. So this is something that about the Elnet setup that Eric Barton suggested. We set up the Elnet networks in that way that we used one TCP network between the two sites for data and one for metadata. Another next step would be to put some quality of service agreements on these Alcatel-Lucent equipment to route the metadata traffic with a different priority or with a higher priority to have the metadata better processed. But as we were shooting only for bandwidth at first, we didn't make that a priority and haven't done this yet. So yeah, basically we have the TCP network for the HP servers, and then we have each cluster attached via InfiniBand to the HP racks. So at the end, we ended up with 21.9 gigabytes a second by writing to the other side. So writing from Dresden to Freiburg and writing from Freiburg to Dresden. Reading was faster. If you divide that by 2, you get something close to 11. And reading from one side to the other side, so just a unidirectional test, ended up at 11.8 gigabytes a second. So reading is a bit faster. But we had some routing issues here on that InfiniBand connection that we couldn't solve. So pushing out the data from the Freiburg cluster was easier than getting data into the Freiburg cluster. That's why we wrote data at the end. And we have to say that the last file system that was on the testbed was the Fraunhofer file system. And Bernd Schubert, a former DDN employee, is now programming the Fraunhofer file system. He has shown, I think, 22.4 gigabytes a second bidirectional bandwidth. So they've beaten us in the last minute on the system, which is nice. Yeah. In Jena, they wanted to see how Elnet behaves on a on a WAN link, but undisturbed we had our own fiber, our own network equipment, no one else on the line. And if you provide links to the whole continent here, then you need to tell people that's how your bandwidth will look like under ideal conditions, and you get like 10% of it. Do something about it. And so they wanted to know what Elnet can do under different conditions with different RPC supply, different latencies. During the project, we got the chance to, or let's say we got some cable boxes in our and some optical amplifiers in our computer room, and could extend the line to 200 and to 400 kilometers. Yeah, and another idea there for Indiana was to compare real latencies at 400 kilometer with latencies created by the NetEM kernel module, which tries to emulate a latency. So what one of the, let's say we're still in the process of looking through data. One of the graphs right now is that we can saturate a link with at 400 kilometer, which is which in our case has like 4.16 milliseconds latency if we have about 12 parallel RPCs. If you look at this number, there was a talk given before, and one of the statements was that you need to know what to expect and such before you do any measurements. So an Elnet test with a single RPC in flight. Take a single RPC is a megabyte, so on a gigabit link from a node to the network, it takes about a millisecond just to transfer the data. You have 4 milliseconds latency, so round trip time for a single RPC should be about 5 milliseconds. So you can do this in, you can do 200 of these packets in a single second. So you would expect the number to be, at 200, not at 100. So I think these, half of the expectation is what Lustre adds to the file system, or to the TCP layer here. But that's all the bad news. The good news is it scales linearly until we have enough parallel streams and can satisfy the link. So we needed, these are I think the best numbers we've seen on the network. We can reach 12 gigabytes a second with let's say kind of unusual combination of Elnet readers and writers. If we use a, let's say, more natural combination, we end up with 11. So I was interested in evaluating how interactive a file system can be. So if we define interactivity, or if we define a acceptable response time from a file system with like 0.1 seconds, where a user can still sit in front of his editor and do stuff, I was interested in how interactive this thing will look if we go from a local server to the file system, if we go with 200 kilometers distance to a file system, if we go from 400 kilometers and look onto the file system. I used IOZone to run to Openeth file and write 64 kilobytes. Here is a megabyte, 2 megabyte, 4 megabytes, so it's a logarithmic scale. And what I've put into that graph is the latency that is needed, or the time that is needed to create the file and to write this amount of data into the file. So what you can see is as you increase the stripe size up to a megabyte, all graphs look the same. So independent from the number of stripes, if you write to a file less than a megabyte, you always end up with something that is slightly above the latency. If you add stripes to this, you see with a second stripe, you have 2 times the latency. With 4 stripes, you have 4 times the latency, and so on. And if you have more than a single megabyte to write to each stripe, you get an additional penalty. In that environment, we had Lustre, the client-side caching enabled. So this is something what I didn't expect. It's okay to create the stripes on a server, but where does this latency come from? Because I expected the data just to go into client-side cache and be done. So this first graph was for 200 kilometers. This is a graph for 400 kilometers. Looks pretty much the same, except there's a measurement error in here, most probably. If you try to model this, and you get some candidates, what can be model parameters in here, and come up with a number of models, put that in your algorithm toolbox, and run an optimization algorithm over it. I figured out that the best model up to now has basically 2 components. First, you pay a penalty per stripe. Second is that you pay a penalty per megabyte that you transmit, which is the inverse of the outbound network bandwidth of the node. And this tells me basically 2 things. First, for each stripe, the client contacts the OSS servers in a sequential fashion, which is pretty bad for WAN, especially for larger distances. And the second thing is, even if I have client caching enabled, I have to wait on the client side until the file data is on the wire. This is something I don't understand as well. It might be a tunable, which I've missed. But it definitely looks like that Lustre is still sending the RPC and then returning from the system call. OK, that was my last slide. Yeah, the test equipment was pretty stable. I think we had a few outages of the 100 gigabit card on the router, but it was better equipment. It's okay, to fail like once a month. You pull the card out, you plug it back in, it started working again. We could successfully tune Lustre and work with that, but we've got beaten by the Fraunhofer file system. And yeah, I completely skipped over the part where I would have explained our monitoring tools, how we tune the system, how we generate program traces and optimize things. I think we moved the questions to the WAN panel.